Hi, we are Jigang Kim and Daesol Cho from Seoul National University, and the paper is entitled, Demonstration-Free Autonomous Reinforcement Learning via Implicit and Bidirectional Curriculum. RL has enabled learning of complex skills solely from interactions with little to no prior knowledge. However, it assumes an episodic setting where resets to the initial state are readily available. Existing methods are ill-equipped for autonomous learning of embodied agents which involve continual, uninterrupted interactions and often require costly external interventions to simulate resets. The videos show some examples of interventions when training robots in the real world. The recently introduced autonomous RL framework formalizes the non-episodic setting where the agent must continuously learn without external resets. Although various ARL methods have been proposed, they rely on prior data to jumpstart and guide the learning process. While a few can operate without demonstrations, there is a significant performance degradation in practice. In this work, we propose a demonstration-free ARL algorithm via Implicit and Bidirectional Curriculum, IBC, that consists of an auxiliary agent and a bidirectional goal curriculum. By adopting curriculum learning, IBC achieves state-of-the-art performance against previous methods, including even the ones that leverage prior data. Here is a conceptual overview of IBC. IBC alternates between the agent of interest and the auxiliary agent during non-episodic training to effectively subdivide a single continuous interaction into multiple forward and backward episodes. The auxiliary agent is tasked with returning to the initial state to provide a strong anchor in the non-episodic setting, and it gradually fades away as the agent of interest improves. When the agent of interest is fully capable, forward episodes are rolled out consecutively without the auxiliary agent intervening for better sample efficiency. The proposed bidirectional goal curriculum is based on optimal transport and is generated autonomously without prior data. It provides additional guidance to the agents by simultaneously generating appropriate goals that converge towards the respective target goals for the forward and backward episodes, row target and row zero target. The conditionally activated auxiliary agent provides an implicit curriculum by shaping row 0F, the initial state distribution of the forward agent, from row 0 target to row target. Initially, the auxiliary agent is always activated and the auxiliary goal row 0 target, which is the last state of the backward episode, becomes the initial state for the subsequent forward episode. Eventually, the auxiliary agent is never activated and row target becomes the initial state distribution of the forward agent. We set row target to row star, the state distribution of the optimal policy that achieves the evaluation goal G-eval, based on the theoretical grounds that row 0 close to row star enables efficient training in RL. In practice, it suffices for row target to contain a minimal number of key points SG star that roughly outline the task. For example, a handful of examples from row 0 and G-eval, respectively. However, the agents may not be able to reach their respective targets row target and row 0 target right away. Thus, we need to autonomously generate intermediate goals for both the forward and auxiliary agents by sampling from the replay buffer. Under the Lipschitz continuity assumption, the goal-conditioned RL objective can be relaxed into the following lower bound maximization form where the task denoted by T* indicates the original targets. We adopt a sampling-based approach to convert the goal curriculum optimization problem into a tractable form and solve the bipartite matching problem with minimum cost maximum flow algorithm to obtain the forward and backward curriculum goals. We compared our method against prior ARL methods across 6 environments. IBC was able to outperform existing ARL methods without relying on demonstrations and achieve comparable final success rates as the Oracle. We also observed that existing methods perform noticeably worse without demonstrations. Here are the visualizations for the implicit and bidirectional curriculum for the fetch, pick, and place environment. As expected, the auxiliary agent intervenes less as the forward agent improves. Likewise, the forward and backward curriculum goals indicated by the red and blue dots converge to their respective targets both qualitatively, in the top figures, and quantitatively, the bottom graph, as training progresses. We also conducted a ablation study and note that removing the bidirectional goal curriculum and auxiliary agent proposed in this work degrades performance. Thank you for listening. The source code for IBC is available on GitHub.